Welcome back. Let's begin chapter number two. Chapter number two obviously is a little bit longer than what you saw on chapter one, so we're gonna break it into sections. So this is the first video for chapter number two. Chapter number two, we are going to be discussing measurement and problem solving. And let's begin with this. So what do we see here? We see a thermometer that sets 34.4 degrees Celsius. We see a cup in two different units of measurements. We can see that one cup equals 237 milliliters. And then on top is one of the things that I really love whenever I travel to Puerto Rico. The gasoline is super cheap, 29.9 cents. That's all the gasoline costs. However, if you know that you're in Puerto Rico, you know that they're using the metric system. So that's 29.9 cents per liter. So to change that to gallons, you're gonna have to multiply by 3.78. So that's what we're doing on this chapter. We're learning about the system of measurements, and we're also learning about how to convert from the English system, which is the one we use here and only one or two more little most countries in the world, and the metric system, which every other civilized nation use. So objectives. So these are the objectives that we're going for. Number one, express very large and very small numbers using scientific notation, and we're going to see what scientific notation is all about. Number two, report measured quantities to the right number of digits. Determine which digits in a number are significant. So we're gonna learn when we measure something, how do we know which numbers we really have to care for and which numbers are just trash? Number three, recognize and work with the SI, that means System International, International System in French, base units of measurement, prefix, multipliers, and derived units. We're talking about like milliliters, grams, kilograms, megabytes, gigabytes, terabytes. Those little words we put at the beginning of a unit to indicate that it's a big or a small unit. Compare between units. So like you saw before, in Puerto Rico, the gasoline is 29.9 cents per liter. So we can convert that from the metric to the English system by multiplying by 3.78 gallons, liters for every 1 gallon. Number five, convert units in a quantity that has units in the numerator and the denominator. We're talking about like I ran this morning at a speed of 8 miles per hour. So how can we convert that to kilometers per hour or miles per minute and stuff like that? And numbers with numerators and denominators. And convert units raised to the power. If my house is 2,300 square feet, can I convert that to square meters or something like that? And calculate the density of a substance. Density is nothing more than the mass of something divided by the space that it takes. Mass divided by volume. And we're going to use that as a conversion factor. A conversion factor is something that relates to numbers. Like I just said, 3.78 liters equals 1 gallon. So 3.78 liters over 1 gallon, that's a conversion factor. For this particular video, we're only gonna focus on objectives 1 and 2. So let's begin with objective 1. Express very large and very small numbers using scientific notation. However, before we even go into that, I believe it's extremely important that we understand why we have to use scientific notation. So let me share something with you. Let's see how I got there.
Well, two people should have.
Well, this is free, so we're gonna have to see
Maybe we should learn a few songs.
advertisement for a short second. So this is, I apologize for that. This is what I want to show you. It's basically what we call the scale of the universe. Pay close attention to the bottom right corner where it says 10 to the minus 6 to the minus 7 and so on. As you can see, as the number gets bigger, we're going deeper and deeper into smaller things. So having a negative number, a 10 to the negative number, indicates that it's a small number. For example, we can see that a quark is almost 10 to the minus 18. Quarks and high energy neutrinos and so on are really, really small particles, even smaller than electron, proton, or anything like that. And then we can continue going smaller and smaller until as far as we can go with the technology we have, which is 10 to the minus 35. And then quick back to our reality. So this is the scale that we see, 10 to the 0, so basically multiplied by 1. And then we're gonna go bigger. And you can see how smaller we're getting. Keep that in mind because that's important from a philosophy point of view. So 10 to the 10 to the 5, we're talking about the size of states like California. And in relation to that, we are already insignificant. And imagine how small we are. So compared to this, what we're seeing on the screen right now, we are like a microwave is to us. And imagine how human beings, in that relationship, we have the power to visualize our universe and try to explain it. So that's very important to understand, the power of our thinking brain. And we're talking about 10 to the 17 now, we're at the galaxy level. So you see how it would be really hard to express this number unless we're using these powers, 10 to the 20, 10 to the 21. So the universe is huge compared to our reality. And we still 10 to the 23 and we can go further. And one of the recent telescopes that we just sent out, that's as far as we can see, which is about 10 to the 27. And then we go back to our reality. So think about how insignificant we are in relation to the big things that we can see, and how awesome we are in relation to the small world that we can also measure. So going back to the scientific notation. So what is scientific notation? Scientific notation is a way to express small numbers and big numbers. So a small number would be, for example, a flea, which measures 0.0032 meters, or a virus, which measures 0.0000000020 meters, or a very big number. It could be our galaxy, the Milky Way, which measures 5 with all those zeros after it. By the way, when I tried to find this information, the only thing I was able to find in Wikipedia was that the radius of the Milky Way is 52,850 light years. And that's not a measurement of size for me. It's more like a measurement of speed. So I had to find out that 1 light years equals 9.46 10 to the 15 meters. And that gave me that many meters. So those are really small numbers and really big numbers. So every time I'm going to talk about the Milky Way, am I going to have the desire to put so many zeros after it? No, so I'm going to use scientific notation. Scientific notation is nothing more than a coefficient multiplied by a power of 10, like you saw in the previous video, at the base of 10 multiplied to some type of power. So let me give you the first trick that we're going to use to make this easier. Between this number and that number, which one is bigger than 1? Bigger than 1 is going to be definitely that one. So whenever you have a number that is bigger than 1, you're going to put the coefficient, you're going to multiply by 10, and that number is going to be a positive number. This number and these numbers, they're less than 1. So whenever you have a number that is smaller than 1, you're going to put the coefficient, and you're going to put the 10 to a negative number. Having a negative power on the 10 means that the number is smaller than 1. Having a positive power on the 10 means that the number is bigger than 1. So with that said, let's take the flip first and convert it into scientific notation. So we know that we have 0.0032. We know that that is smaller than 1, so that we know it's going to be negative. And this number, the coefficient, has to be between 1 and 10. So this is definitely not 1 or anything between 1 and 10. So we're going to take the decimal point and we're going to move it until we make it look between 1 and 10. So when we go like this is giving us 3.2. So that's between 1 and 10. And how many times did we move it? We move it 1, 2, 3 times. So that's where the 3 goes. So that's how you write that number on scientific notation. First thing, you determine if the power is going to be positive or negative. If the original number is bigger than 1, then like the galaxy, then the power of the 10 is going to be positive. If the number is smaller than 1, like the virus, then the power of the 10 is going to be negative. Then you take the number and you move the decimal point to whatever direction you need to move it so that you can make it look like between 1 and 10. On this case, we move it to the right 3 times to make it look like 3.2, which is between 1 and 10. Let's go ahead and do the virus now. So the virus is 0.12, 1, 2, 3, 4, 5, 6, 7, 20. We're going to put the coefficient, multiply by 10 to a negative power because that number is smaller than 1. And then we're going to move if we go this way, that's never going to make it between 1 and 10. So that's not what we're doing. We're going to move it this way. 1, 2, 3, 4, 5, 6, 7, and 8. So that's where the 8 goes. And once we do that, then this is going to be 2.0. Now let's do the galaxy. The galaxy is bigger than 1, so it's going to be positive. If it's positive, we do not put the positive. So we're just going to leave it like that. If you don't see a sign, that means it's positive. So that number doesn't have a decimal. So if you don't see a decimal, that means that the decimal is at the end. If you don't see the number, the decimal then has to be at the end. So we're going to move it until we make it a number between 1 and 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20, which means we move it 20 times. We know it's positive because the number was bigger than one when we start with. And by the time we finish, we're gonna put 5.0. Do we have to put every zero in there? No. That's the reason we are using scientific notation, so we don't have to write all those zeros in there. If it wasn't zero, then we can probably put those numbers in there. It's gonna depend on what we're doing. So that's how we write scientific notation. That's how we take a small number and change it to scientific notation, negative. That's how we take a big number and change it to scientific notation, positive. So if you have any question on how to do this, watch the recording again. If not, watch some of the tutorial videos that are posted on Canvas. And this is your first daily work. So once more, at this point, you pull out a piece of paper, you put DW 2.1, it has to be labeled, and you put the answers in there. You can write the problem if you want to, or you can just put the answers as long as you show me your work. So you can stop this, put it on pause or something like that, and do it, but I'm gonna continue right now. You can do that later. Or right now while you're watching it, right? You put it on pause and you do it, and then you listen to me again. So that finished the first learning objective. Express very large and very small numbers using scientific notation. Let me know if you have any questions. Second objective, measure numbers. So we're gonna work now with measure numbers. What are measure numbers? Those are numbers that we get from something that we measure with an instrument. For example, on this first one, I'm measuring the mass of that liquid on a scale. So that's a measure number. It's telling me that this mass measures 95.85 grams. So this will be a mass. I can also measure temperature. And notice that this particular instrument allows me to measure in degrees Celsius, Fahrenheit, and degrees Celsius. I can also measure time. And this instrument appears to be measuring seconds and fractions of seconds. I can also measure volume from liquids. And I can also measure length, so how long something is. Those are the 5 most essential types of measurements that we're gonna do on this course: mass, temperature, time, volume, and length. And on our next objectives, we're gonna learn the units that we use to measure that. Like mass could be grams, could be kilograms, could be milligrams, micrograms. Temperature could be Fahrenheit, Celsius, or Kelvin. Time could be hours, minutes, seconds, days. Volume can be liters, milliliters, cubic centimeters, cubic meters. And length could be meters, inches, miles, anything that indicates length. So a measure number is nothing more than something that you measure with an instrument. Therefore, that number is a measure number. Makes sense, right? So what's gonna be the learning objective with measure numbers? We're gonna report measured quantities to the right number of digits. And we're gonna determine which digits in a number are significant. So what does that mean? Well, if I'm measuring the mass of this, it's telling me that the mass is 95.85 grams. This is a digital instrument. So whenever you have a digital instrument, everything it gives you is significant. So on a digital instrument, whatever the display gives you is a significant number. And it's reporting it to you directly. So that's an easy one. If it's on the screen, you report that number and everything is significant. What about this one with volume? Notice that this one is increasing as we go down. So on this one, we're gonna have to look at the scale. So this is gonna be 8. This is gonna be 7. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we have 10 units in between. So that tells me that this first line is going to be 8.1. This one is going to be 8.5. This one is 8.9. So I have determined that every line between the big numbers is going to be equivalent to 0.1. And I'm assuming we measure in milliliters because we measure in numbers. So that's the first thing you do. When you have an instrument like that, you have to determine the value of each small line. In this case, since we have 10 lines between the 7 and the 8, each line is 0.1. So how do we report this measurement then? So that's what we're doing, right? Reporting the measurement. So since this is a liquid, notice that the liquid forms like a curve right in there. So let me show it to you better here. So if we have a liquid, most of the liquids are gonna have like a curve in there. We call this the meniscus. The meniscus is the curved portion of the top surface. And that's what we measure. We're measuring where that curve is located. So where that curve is located is right there. Let me do that again. That curve is located, say right there. So what do we have? Well, we know that this is 7, 7.1, 7.2, 7.3, 7.4. So we know it's definitely 7.4 because it goes past that line. However, it doesn't make it to 7.5. So somewhere in here, I'm gonna have to estimate where it falls. And I see it kind of halfway. So I know it's 7.4, past 7.4. I know it's before 7.5, and I tend to see that it's kind of halfway. So I'm gonna say, on my mind, I'm gonna take between 7.4 and 7.5, and in my mind, I'm gonna break it into 10 small similar places. So I'm gonna estimate that that's gonna be, if I have 10 lines in there, then that's gonna be halfway, which is 5 lines. So for this particular measure, I'm gonna call it 7.45. But what is one of you tell me, you know what, Mr. Reyes, I disagree with you. I think it's 7.46. And what if another one of you tell me, well, Mr. Reyes, I think you're wrong. I do not see 7.45. I see 7.44. And that's all good because we can only say with certainty those lines. So what lines do we have? 7.4 and 7.5. So we know the 7 is significant because we know for sure it's 7. We know that the 4 is significant because we know it goes past 4. And that's the same for me. Everybody's agreeing on that. So we call those certain digits. The ones everybody can agree on, that's what we call a certain digit. The one where we're having our differences, that's what we call a estimated digit. So any measurement that you take with any instrument, the last digit is always the estimated digit. So going back to the question, how can we report this number? Well, this number can be reported like 7.44, 7.45, or 7.46. Any of those three would be good because the last digit depends on your estimation. What about determining which digits in a number are significant? Well, the 7 is significant, the 4 is significant, and the 4, 5, or 6 are also significant because it's telling us that we are estimating. So which numbers are significant on a measurement? Any certain digits, the one everybody can agree on, and the last estimated digit. So on this particular case, this instrument can measure to 2 decimal places. So from here on, whoever uses this instrument until the instrument breaks apart will always have to measure 2 decimal places because that's what we decided based on our reading that this instrument can do. Going back to the scale. So I told you everything that the display gives you is a significant number, and that's true. But I also told you that any measured number, the last digit is the estimated number. So I want you, whenever you start using the scale that came with your kit, I want you, whenever you use the scale, to look at the last number and notice that every so often it fluctuates, it changes. That means that the machine is estimating the last number. So any measurement, it doesn't matter if it's digital or not, the last digit is always the estimated number. So that brings us to a little more detail. So on this case, you have the instruments and you can read it, right? What happens if somebody gives me a number and somebody said, you know what, I just measured this and this measures 35.5070000 meters. So how do I know which numbers are significant? Well, if you go to your textbook, you're gonna see that there's like 7 rules that tells you how to determine that. If you have a sandwich number, a sandwich zero, basically a zero between 2 numbers, that's significant. Any number, 1, 2, 3, 4, 5, 6, 7, 8, or 9, any digit, which is what we call a number, is significant. So this is significant, this is significant, this is significant, this is significant, and this is significant. Then we have the 0. The 0 is not a number. The 0 is a placeholder. But if this 0 is between 2 numbers, then the 0 is significant. If these zeros are after a decimal place, then we have to see. If we have a 0 before a decimal, so there's a lot of rules. So this is what I want you to do. Forget about that. Let's do the easy way. A very wise person showed me this long time ago. So how do we can always, without failing, determine how many significant digits a number have? Well, we're gonna use this analogy. We're gonna do something like this. And I'm gonna say, to the best of my abilities, that this is the map of the United States of America. And on the right side, I'm gonna have the Atlantic Ocean. And on the left side, I'm gonna have the Pacific Ocean. So Atlantic on the right, Pacific on the left. And then this is the analogy we're gonna use. Present and absent. What am I talking about? I'm talking about the decimal place. If I have a number like this, the decimal place is absent. It's not in there. You don't see it. So it's absent. So the analogy is that we're going to determine is the decimal is present or absent, and then we're going to go to the United States. So we always go to the United States. So this number, in which the decimal is absent, we're going to count significant digits from right to left. This number, in which the decimal is present, we're going to go from left to right. And the only numbers that are going to count are so what we're going to do, we're going to go from right to left, and we're going to start counting as soon as we find a number. 0 is not a number. Keep going. Right here, we found a number, so everything counts. So this number have 4 significant figures. So once more, determine if the decimal is present or not. If the decimal is absent, start counting from right to left. If the decimal is present, start counting from left to right. And begin counting the moment you find a number. And these are my numbers. The 0 is not a number. So let's do this one. The one on the left, we're going to start going from left to right. So not a number, not a number. Here is my first number. So everything counts. Once you find a number, everything counts. 1, 2, 3, 4, 5, and 6. 6 significant figures. And why is that? Why only six significant figures? Because this number here basically do not count. They tell you how precise something is, but they're not really significant on the way that tell us more information. So let's do a few more problems here. Let's say that I have 303, and I have the map of the United States, Pacific and Atlantic, to the United States, to the United States. On this number, the number is absent, so I'm going to go right to left, and I'm going to start counting the moment I find a number. Right there, 1, 2, 3. 3 significant figures. 0.1340. There's a decimal present, so I'm going to go left to right, and I'm going to start counting everything the moment I find a number. What about this number? The decimal is absent, so I'm going to go from right to left, and I'm going to start counting the moment I find a number. So 1 significant figure, and so on. So make sure you practice that. If you do that, you can forget about leading zeros, trailing zeros, sandwich zeros. You can go from 7 rules all the way to this analogy. So here's your daily word number 2. So the first thing I want you to do is to look at this here, and based on that scale, read it. Remember, you always need an estimated digit at the end. For example, let me show something I forgot. If you have something like this, 1 and 2, and you have 10 lines in between, we know that at least each line is 0.1, right? So we know that if something falls in between the lines, on this case, this is going to be 1.45. So we know that this instrument this is certain, this is certain, this is estimated. This instrument, you can measure 2 decimal places. So what happens? So what happens when the measurement falls right on the line? So you don't have to be estimated, right? So this will be definitely 1, and it's going to get all the 1, 2, 3, 4, 1, 2, 3. definitely going to be on 4, and we don't have to estimate it because it's right on the line, but we already decided that this instrument measured 2 decimal places, so you're going to make sure that it shows 2 decimal places. So for daily word number 2, use that technique, determine how many decimal places you need, and then make sure that it shows on all measurements that you do. So what would be the measurement for number 1? Make sure you put the units in there also. Always include the units. What would be the measurement for the number 2? Remember, you measure it on the meniscus. And then on number 3, using the analogy that I gave you with the map, or just using all the rules, determine how many significant figures you have on each one of those numbers. So in science, remember we talked about the scientific method earlier. In science, we do measurements and then we have to do calculations. So what happens when we do a calculation like this one, and my computer or my calculator give me a whole screen full of numbers? Is that truly my answer? And the answer is no, that's not truly your answer. Your answer is going to be based on the numbers that you're using. And why is that important? That's important because when we combine different measurements, the final measurement is going to be dictated by the best measurement. For example, if I measure something on a scale that cost me $1 million, that scale probably going to give me like 10 decimal places. And then I measure something else on a scale that cost me $100, the scale probably going to give me only 1 decimal place. And then I do a calculation where I have to combine these numbers. The moment I combine those numbers, who cares if I pay $1 million for one of the scales? My final number has to show the least precise number. So I'm going to have to go based on my least precise number, which is also the number with the least amount of significant figures. So in case of multiplication, actually let me begin. Let me begin not with multiplication, let me begin with an addition. One way to see this is like this. 0.987, you're adding that to 125.1, and you taking away 1.22. So the more digital numbers I have, the more precise the number is. So this is my best measurement, and this is my worst measurement. So whenever I do that result, this is going to give me 7. This is going to give me plus and minus. This is going to give me 6. This is going to give me 8. This is going to give me 4 and 1, 2. So that, if I put all that on the calculator, this is what I'm going to get. However, I have to make sure that my final result reflects the worst unit. And in this case, the worst unit have only 1 decimal place. So the rule is, when you're doing addition and subtraction, the final result have to have the same amount of decimal places as the one with the minimum number of decimal places. So in this case, this will not be my answer. My answer would be 124.8. So I'm going to cut the 6 and the 7. But we have to review our rounding rules. The rounding rule says that if the first number that you throw out is bigger than 5, then these have to be rounded up. So my answer would be 124.9. So once more, addition and subtraction, your result has to show the same amount of decimal places as the measured number with the least amount of decimal places. On this case, 1 decimal place. What about multiplication and division? For multiplication and division, the rule is a little bit different. For multiplication and division, we're going to count significant figures. So there's a decimal here. So we're going to go from the Pacific left to right. So this is going to have 4 significant figures. This one is going to have a decimal. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 significant figures. And this is our answer, 0.776610. So the more significant figures you are, the better your measured number is. So we're going to stick to the one with the least precision or the one with the least amount of significant figures. So my answer is going to have to be 4 significant figures. 1, 2, 3, 4. So we're going to cut it right there. This number is less than 5. So we're just going to cut it and do not do anything to the remaining number. So if the number that you drop in is less than 5, do not do anything to the resulting number. What about the last one? On the last one, first thing, we're doing multiplication and subtraction. So this is going to have to be 2 steps. You're going to have to determine, remember, we always do parentheses first, right? You're going to have to determine the number of resulting significant figures there. Then you're going to do multiplication, so you're going to have to compare. So 5.67, 2.3, that's a subtraction, 2 decimal places, 1 decimal place. So we know this number is going to be only 1 decimal place. So that's going to be 4.4. Let me see, 7. Sorry, let's do the. Let me do it. Make sure I can see it. 567 minus 2.3. That's going to be 7. That's going to be 3, and that's going to be 3. But we're going to leave it at 1 decimal place. So this is going to be 3.4. So the number that's going to come out is going to be 3.4. But hold on, do not do anything yet. So now it's going to be 3.489 times 3.4. So my result is going to be 4 significant figures multiplied by 2 significant figures. So my result is going to have the least amount, 2 significant figures. But there's something that you have to keep in mind. When you have combined operation like this, we're not going to do this and say that it's 3.4, sorry. And then do the multiplication. What you're going to do, you're going to do every single number. So 3.37 multiplied by 3.489. And then when you get the result, you're going to make sure that it only has 2 significant figures. So when you do combined operations, mentally determine how many significant figures you're going to have to have at the end, but put all the numbers on the calculator. Do not cut it to 3.4 first and continue. Just put all the numbers on the calculator, but be aware that at the end, you're going to have 2 significant figures only. So since we don't have the opportunity for you to ask questions and I can answer them to you right here, right now, if you need to go back on the video, re-listen to it. If me repeating the same thing over and over doesn't do it for you, go watch the videos on the tutorial videos, or go to the book and see all the examples that we have on the book. And that's what I said. Having all these 3 modalities allows you to understand this better. You could be a reader, or you could be a better listener, or you can be a visual. So with that said, then this will be your daily work 2.3. You're gonna have 3 problems. It's multiple choice, so once you do it, you can determine. On the first one is multiplication, the second one is addition, and the third one is one of those combined operations. So with that said, we're gonna say that we covered this objective: report measured quantities to the right number of digits, determine which digits in a number are significant. It's up to you to be honest with you and say, I didn't get that, so come to my office, go to the Science Learning Center, send me an email telling that you want to meet with me on Microsoft Teams online so we can talk about it, or watch the videos, read the book, go to the 24/7 tutor section where you can talk to anyone any day at any time, or watch the tutorial videos. And this is where we're gonna stop this first video. So at this point, these are the concepts we cover: express very large and very small numbers using scientific notation, and know how to read a measurement, and know how to distinguish which ones are my significant digits or significant figures. So next time we meet, that's where we're gonna start the next objective. We have 5 more objectives to go. We probably do 2 more or 3 more on the next one. So we're gonna try to break it so it doesn't go for too long. So that said, please email me if you have any questions. Take care.